Hi students, welcome to Algebra 2C. This is Mrs. Brunk. And since this is the first lesson of Algebra 2C and possibly your first class in a flipped classroom, I just wanted to take a few moments to quickly go through the expectations when you're watching the videos. Many of the expectations that I have for you while you're watching the videos are the same things that we would expect to see you do in class. Number one, that you're an active listener and a participant, that you're listening closely to the concepts, that you're taking notes where indicated, and if you have extra things you want to write down as well, there is space provided here in your guided notes for those. If we have problems that I ask you to try, sometimes I'll ask you to try them as part of the outside of class work, and we'll call those you try questions. And sometimes I'll say they're you try in class, and those will be how we'll start the following class period to test your understanding of material. But the expectation is if I do ask you to pause the video and try a problem, that you do that. As well as if we have a warm-up, there is a purpose for every warm-up. The warm-up is to kind of key on prior knowledge and things that we'll be using in the lesson on that particular day. So expect that you pause the video and try those warm-ups. And that you make a note of the things that you feel really confident about and the things that you're struggling with, so that when we do meet in class, you're better able to access the help that you need. And so, again, the expectation is that you're just an active listener, that you're paying close attention to the things that are your strengths, as well as the things that are your struggles. And you come to class, the next class period, ready to really make sure that you clarify those things that you're struggling with. Now, I just spoke about a warm-up, and if we do have a warm-up, I expect that you pause the video and give that a try. So there is a warm-up for this lesson, so please pause the video now and complete the warm-up, which asks you to solve each of the equations for y. So please pause the video now. Okay, so thanks for taking some time to try the three warm-up questions. Take a moment and check your answers. And if for some reason one of them or more are incorrect, what you should do is pause the video and look through the solutions and see if you can figure out where your mistakes were made. And if you're unable to do that, then make a note so you can bring that up when I see you in class. So lessons usually start off with us identifying our learning goals or our benchmarks, the objectives of our lessons. And we have two of them today. We're going to be graphing and recognizing inverses of relations and functions. And secondly, we're going to be finding inverses of functions. So we're going to learn to identify them, the inverses of relations and functions, and then we'll also learn to find them. So you've seen the word inverse used in many different ways. For instance, we have talked about the additive inverse. And so the additive inverse is the number that you add to a number to get 0. And so our additive inverse of 3 would be -3. So there's additive inverses. The multiplicative inverse, when we talk about multiplicative inverse, that's another way of saying reciprocal. And what we mean by the multiplicative inverse, we mean the number that another number can be multiplied by to get to 1. And so the multiplicative inverse of 5 would be 1/5. Or if I wanted to know the multiplicative inverse of 3/2, it would be 2/3. We've talked about the inverse of a matrix, and we studied those when we were solving systems. And you may remember that the formula for that looked like this. We found that by finding the determinant and then multiplying 1 over the determinant by what I call the switch ops matrix, which really takes the elements of a 2x2 and switches the first diagonal and then changes the sign on the terms in the second diagonal. So we call that the switch ops. In this lesson, we're going to be looking at inverses of relations and of functions. So it could be just as simple as a relationship represented by some ordered pairs, and we could find the inverse of it. And we can also find the inverse of functions, like this linear function, f of x is equal to 2x minus 9. Now, essentially, when we talk about the inverse of a relation or a function, it's like we're just looking at the relationship from the other variable's perspective. And so to actually graph the inverse relation, we can simply, if we had a graph of the original relation or the original function, we can simply just reflect each of its points across the line y equals x. Because essentially what we do to find an inverse is we switch the x and the y values. So when we think of inverse, we can kind of think of reverse. Reverse the x and the y. So let's take a look at finding the inverse of some relations and some functions. So we'll turn the page to do that. Okay, so let's take a look at example 1, graphing inverse relations. So we're asked to graph the relation and connect the points. So we're given this set of ordered pairs, and we don't know if there's an equation that actually describes them or not. We just know that this is some sort of relationship between two variables, x and y. And so if we wanted to graph them, we could just simply plot those points. So for instance, the first point is 0, 2, so we would plot 0, 2, which would be right here. 1, 5, so that would be right here. 5, 6, right there. And then 8, 9, so that would be right here, 8, 9. And then we're asked to connect those with a dotted line. Now the reason why we're going to use a dotted line when I connect these is we don't know for sure that all of these points between these ordered pairs that we graphed actually exist. But just so we can kind of see the trend of the line, we connect it with a dotted line. Because we don't want to like represent this as a continuous function, because we don't even know if it's really a function. We just know it's some sort of relationship between these two variables. So next we're asked to graph the line y equals x. So you may remember that the line y equals x is the line that just cuts straight through the first and third quadrants. Because basically what it's saying is no matter what your x coordinate is, your y coordinate will be the same. So you'll have points on that line like say -2 and 2, negative 2, and 0 and 0, and 2 and 2. So whatever you pick for the x value, the y is exactly the same. And so if we were to plot some points like that, like 0, 0, I can't really plot the negative 2 on my particular graph, but you know, say 4 and 4 and so on. And so I plot those points 0, 0, 2, 2, 4, 4, and so on. The line that I would draw would split down through that first and third quadrants. Now, if we were to take and reflect those points over this line y equals x, we would get the inverse of this relation. And how we actually reflect those points over is essentially just by switching the x and the y values. So we're essentially going to take this table and we're going to flip-flop the x and the y. So instead of the point being 0, 2, it's going to be 2, 0. And instead of 1, 5, it's going to be 5, 1. Instead of 5, 6, it's 6, 5. And instead of 8, 9, it's 9, 8. And if we were to plot those points, 2, 0, which would be right here, you can see that's the reflection of that point 0, 2. The point 5, 1, so there's the reflection of the 1, 5 is 5, 1. That's that point's reflection right here. See, we're basically just reflecting each point over. The next one would be 6, 5, so that's right here. And then finally 9, 8, so there's 9, 8 right there. And then we could connect those, again with a dotted line. And you can see that not only are the points the reflections of each other over this line y equals x, but the trend, the graph, the shape that it makes is a reflection over that line as well. So when we have a relation, the way that we find the inverse is by switching the x and the y coordinates, which is basically equivalent to just reflecting over the line y equals x. So we've reached our first you-try question. So we're going to designate this next one as a you-try question. I'm just going to, and this seems like a pretty easy task. So we're going to have this one be a you-try, not a you-try in class, but you-try now. So I'm going to ask that you pause the video. And essentially the same task that we just did in our example together, I'm going to ask you to do here, to graph the relation and also its inverse and the line y equals x. So please pause the video now and complete the check your understanding or the you try question. Okay, so take a look at your answer and compare it to mine. I did the original in blue again, and I did the inverse, the new set of points I graphed in purple. And of course there's the line y equals x, so you can see the points are simply reflections over that line. Okay, let's go ahead and turn the page now. So that kind of sort of does it for relations, but what about functions? When a relation is also a function, you can write the inverse of the function f of x as f inverse of x. So remember when we see that power of -1 on something, the way that's really read is inverse of. So for instance, when we did matrices, we said a inverse, we said a to the -1, that was read inverse. So when you see that, it's read the inverse of. And so you know, basically what inverse functions do is they undo each other. So you know how multiplying undoes dividing and adding undoes subtracting and things like that. Well, inverse functions will undo each other. They sort of reverse the process. They undo each other. So to check if one function is the inverse of another, you could plug in an x value, so for example 1 or whatever value, in for the original function. And then whatever you get for an output, plug in your answer from that first step into the inverse and see if it brings you back to that original. So for instance, if I were to plug 1, say, into f of x, and I took the output of that and substituted it into the inverse function, the output of that should be the original input value of 1. So let's see if that works for x plus 6 and x minus 6 to see if they are actually inverses of each other. So if I were to take 1, say do f of 1, and I plugged 1 in for x, my output would be 1 plus 6, or 7. And then if I took that 7 and I substituted it in to the inverse, so I did f inverse of 7, then that would mean this was 7 minus 6, which is 1. And so it was the inverse because what it did is it took that original input and gave me that same value as the output. Let's look at another example. So prove that these functions are inverses of each other. So I want to know if f of x equals 3x plus 6 and f inverse of x equals 1/3 x minus 2. And actually they probably technically should not use this notation here because we don't know for sure that they're inverses, but we want to just maybe find out for sure, to see for sure. So let's pick a value to plug in for x. So let's say I wanted to plug in, let's do 2 this time. So if I did f of 2 and I plugged it in, my output would be 3 times 2 plus 6, which is 12. So now if I took that value of 12 and I substituted in what I think might be the inverse and substituted it in for x there, let's see what I get. So I plugged in 12 there. 1/3 times 12 is 4, and 4 minus 2 is 2. So, voila, our original input was the output after we substituted into the original and then the output into the inverse. Well, that's one way to tell. Another way to tell is to actually take the original function and write the inverse algebraically and see if you just don't get the other function. And so this is how we would do that. So to write an inverse algebraically, you simply have to switch the x and the y values. We just talked about that with relations, but the same holds true with functions. The only problem with when we write something in function notation is it doesn't actually have a y. So our first step is to take and substitute back in for f of x what the y, which really is what that means. It means it's just f of x is just function notation for saying y equals. So the first thing we would do is substitute back in for f of x, we plug in the y. And then you switch the x and the y, literally switch the places in the equation. So that's what I'm doing here. So this would make this say x equals 3 times y minus 7. Now that actually technically is the inverse, but we don't usually leave equations solved for x. Because first of all, we can't write it in function notation. If it's solved for x, it has to be solved for y. And secondly, when we graph, that's usually how we see things written. And so our final step would be to actually solve this back for y and then replace the y with f inverse of x so that we've written it in function, or in this case, inverse function notation. So this is what it would take for us to solve it back for y. We'd have to distribute that 3 through. Or we could simply, I guess, divide both sides by 3. But if you distributed the 3 through, that'd be 3y minus 21 and equals x. And then we would have to add 21 to both sides, which would then give us x plus 21 equals 3y. And then to get rid of the y, we just have to divide by 3. Now when you divide by 3, you're dividing everything by 3. And sometimes you'll see people do this. They'll write the whole thing over 3, like that on the other side. But then they might make the mistake of say, oh, I can just cancel that 3 out with the 21. But both terms are being divided by 3. So I think the best way to go about that, what I choose to do, is I will just give each separate term their own divisor of 3. So everything's going to get a divisor of 3. And so then when I go ahead and cancel out the 3 on that side, and I like to usually rewrite it with the y on the left, so I write that as y equals x over 3 is really the same thing as saying 1/3 x, and then 21 divided by 3 is 7. And so then the final step is to go ahead and replace the y back with inverse notation, but since this is the inverse of f, I'm going to write it as f to the negative 1, or f inverse of x, equals 1/3 x plus 7. Now the last step says to check. So one way I can check is the way that I showed you in example 2, where you just pick a value to plug into the original function, and then whatever you get for an output from that, put it into the other function, and going through that function should give you an output of what the original input was. Sounds a little confusing. But another way, remember with the relations, was we looked to see if they were reflections of each other over the line y equals x. And that, I think, is a really good way to do that, especially in the case of these lines, which are lines, they're linear functions. So this is what it would look like if I typed these into my calculator. So what I went ahead and did is I put the original into the grapher in y sub 1, and what I got for my inverse in y sub 2. And then I also put a third graph in. I put in that y equals x, because remember that the graphs are supposed to be reflections over the line y equals x. And so then I graphed them, and you can see that the lines really do look like the reflections over that line. This line right here is the y equals x. And you can see if you identify certain points, like say this point right here and this point right here, you can see that they appear to be, and then the scaling's off just a tiny little bit because it's not a perfectly square window, but they look like they are reflections of each other. And here's another way that you can tell. It's sort of hard to tell from the table, but remember there's the points have to switch x and y coordinates. So I found a pair that did. See, like if you look at the x of 3 and then the output for y sub 2 is 8, and then I looked at the input of 8 and the output of 3 on y sub 1. So you can see how the x and the y coordinates are switched here. And you can't see it as clearly because it's, you know, like if I were to look for, say, the point for -9, then I'd have to look for -9, 4 on the other graph, and so that's down further on the table. But you can see by graphing these that they do appear to be reflections of each other over the line y equals x, and then the points in the table will verify that simply x and y have switched places, which is what an inverse does. So let's go ahead and look at the next page. And here's one for you to try. So I'm going to designate this one as a you try question. And I'm just going to have you go ahead and try it now rather than in class. So I'm going to have you pause the video and take the function f of x equals 5x minus 7 and write the inverse by following the steps that are detailed in the problem. So go ahead and pause the video now. Okay, so the inverse of 5x minus 7 is 1/5 x plus 7/5. And you can check it either way I talked about. Either pick a value to plug into the original, take the output of that and put it into the inverse and see if you get back to your original number. That's one possibility. And the second one is to simply graph them, including y equals x on your calculator, and see if they look to be reflections of each other and verify using the table. So in example 4, we're actually going to kind of put this stuff together, this idea of the graphs being reflections and the equation for the function. And we're going to be asked to write and graph the inverse of functions. So let's just take a look at the original function. F of x is equal to negative 1/2 x minus 5. So that's in slope-intercept form, makes it very easy to graph. So we can simply just plot the y-intercept, which is negative 5. And then the slope is negative 1/2. So we're going to rise a negative 1 and run 2. And we could also rise positive 1 and run negative 2. And that would give us 2 points on this line. So now I'm going to connect them to get the graph of the function. So my graph would look like that. Now I like to draw in that reflecting line, that y equals x. So I'm going to go ahead and just do that as maybe just a dotted line. I'm just going to kind of plot the points that would be on that line y equals x. And just do a little dotted line. And then I know that the inverse should be the reflection over that line. So now I'm going to go ahead and write the function inverse. So I'm going to switch x and y, so I know that this is really just the same as saying y equals. So I'm going to flip-flop x and y. So that's going to be now x equals negative 1/2 y minus 5. And now I've got to solve back for y. So the first thing I'm going to do is add 5 to both sides, which gives me x plus 5 equals negative 1/2 y. And probably easier than dividing by negative 1/2 would be to multiply both sides by negative 2. So I'm going to cancel out this negative 1/2 by multiplying by negative 2, which means I have to multiply this whole thing by negative 2. And then I'd have to distribute that negative 2 through, which would give me negative 2x minus 10, and then equals y. So putting that back into inverse notation, it would be f inverse of x is equal to negative 2x minus 10. Let's go ahead and graph that. So it looks like I'm going to have to extend my graph out just a tiny little bit, so I can do that because it looks like I haven't gone quite far enough to go down to negative 10, so maybe that's going to be negative 9, negative 10. So if I plot the y-intercept, it's at negative 10, and then I've got I could rise a negative 2 and run 1, or rise a positive 2 and run a negative 1. So that's what I'm going to do, is go up 2 and left 1, up 2 and left 1. Continue that until I get enough to make a decent line here, up 2 and left 1. And so if I connect these points, that will give me my line. And there it is. And so this one was the inverse, and then the original one was right here. It was f of x. And you can clearly see that those lines are reflections over y equals x. And so that's our way of verifying that, in fact, negative 2x minus 10 is the inverse of negative 1/2 x minus 5. Okay, let's go ahead and turn the page. And so we have one for you to try now. So if you would pause the video now, and this will be a you try question. So you're to graph the function f of x is equal to 2/3 x plus 2, and then write the inverse and graph it. And be sure to include the line y equals x on your graph so that you have a visual confirmation that the graph is actually the reflection of the original over that line. So please pause the video now and write and graph the inverse of f of x. Also graph f of x. All right, so take a look at the graphs first and make sure that they look like they're reflections of each other, and make sure they look like the graphs that you drew. And then the final answer, which is the inverse, is right here, 3/2 x minus 3. So the inverse of 2/3 x plus 2 is 3/2 x minus 3. So our final example, we're going to be looking at a real-life application. And in a real-world situation, we don't switch the variables. Because in a real-life situation, the letters that we choose as variables actually represent specific quantities. And so really, when we want to write an inverse of a function, in other words, we want it to be sort of the equation to be from the other variable's perspective, we just instead solve the equation for the other variable. So we don't literally switch the x and the y, we just switch which variable the equation is solved for. So there's a little different approach when it's real life because we don't technically want to change the variables around because they represent specific quantities. Here's an example that shows that. So Juan buys a CD online for 20% off of the list price. That's the first thing that's important. He has to pay $2.50 for shipping, and the total cost, or the charge, is $13.70. What is the list price of the CD? So the first thing we would want to do is you want to write an equation that describes the cost. So we know that the cost of this CD is equal to, it's 20% off the list price. So it would be the list price times 1 minus 20, which means 100% minus 20%. So we're not actually paying 100% of the price. We're paying 100% of the price minus 20%. And then we also have to pay this shipping charge of $2.50. Well, if we were to simplify this part of it, the 1 minus 0.2, we actually get 0.80L. So if we're paying 80% of something, we just take that price and multiply it by 80%. Because we're paying 80%, we're only paying 20% less than what the original price is. So that's 80%. And so we know that the cost is equal to this. Well, we want to now actually find out what the list price is. So if we were to take that amount for the cost, and or if we were going to rewrite this in terms of the list price, then we could just substitute the cost in of $13.70, and we could solve to find out what the list price is. So the first thing we could do is just rewrite this function for the other variable by subtracting 250 from both sides. And that would give us the cost minus $2.50 equals 0.80 times L. And then we could just simply divide both sides by 0.80. And that would give us the list price. And so our equation that would be solved for L, list price, is cost minus $2.50 divided by 0.80. So now all we have to do is take that value of $13.70, substitute it in for the cost, and we can calculate the list price. So if we do that, that's $13.70 minus $2.50, which is $11.20, and then divided by 0.80 is 14. And so the list price must have been $14. But then we received a discount of 20% and had to pay $2.50 for shipping, and the final cost was then $13.70. So again, in real life problems, instead of switching the variables, really should just solve the equation for the other variable. Well, that actually does it for our lesson on inverses. So I will see you in class.